All right, so I wanted to make hopefully a short little video here on emphasizing or clarifying the difference between a power function and exponential function, and this type of function here, which is neither a power nor an exponential function, but looks very similar to both of them. So for this, we're going to assume a is a constant, which also means that we're assuming, in this case, it's a real number. We're going to say u is a function of x and w is a function of x, and anywhere we see x, that's just the normal x that we think of. So power functions. A power function is anything that is written in this form, so y equals x to the a, where the base is the variable and the exponent is a constant. We can also have y equals u to the a, where it doesn't have to just be x. Think about, you know, if I have like y equals x plus 5 to the third, right? That's still a power function because the base is a function of x, u, and then the exponent is a constant. Now, the other thing I would like to emphasize about this is I keep using the word constant, I don't say integer. So remember that a lot of times we might think of power functions as polynomials because, yes, polynomials do meet our definition of power functions. However, the a can be a rational number or even an irrational number. You know, I could have x to the pi. That still would be a power function. But I could also have x to the -3/2. That would still be a power function. As opposed to an exponential function where the base is a constant and the exponent is the variable or the input. Remember that exponential functions are the inverse of log functions. And again, I want to emphasize that the exponent doesn't have to just be the variable x. It could be a function of x. But the point is the base has to be a constant that is a real number. And then we have an exponential function. Now, if we have something like this, where the base and the exponent are both functions, or here u and w, where they're both functions of x, this is neither an exponential function nor a power function. The reason why we care so much about this with this unit with derivatives is if something is a power function, then I can use the power rule to do the derivative. So I know that my derivative here is going to be y prime is a x to the a minus 1. Or if I have this one, y prime is going to be a times u to the a minus 1, and then times u prime, which would be the derivative of the inside. So I'd just be doing the chain rule there. And we know from what we just learned recently that if I have y equals a to the x, since this is an exponential function, I can either use logarithmic differentiation, which is how we proved the derivative of an exponential function, or if I know what that is, because I want to just be good at understanding the derivative of an exponential function, then I know that my derivative is going to be y prime equals a to the x times ln of a. And again, if you're confused on how I'm getting that, look back at the video on derivatives of exponential functions. Or here with the chain rule, we have y prime equals a to the u ln of a, and then times u prime or du dx. And now again, I want to emphasize for the exponential functions, what we saw in the derivative of exponential functions video was that we showed this by doing what we call logarithmic differentiation. Now, just to refresh your memory, logarithmic differentiation is where the very first step is for us to take the natural log of both sides of the equation so that we can then bring the exponent down and do implicit differentiation on both sides, and then ultimately solve for y prime. That's what we mean by logarithmic differentiation. If we understand the derivative of exponential functions and we recognize when we have an exponential function, we do not have to continue to do that if we know what the derivative is. But if we don't remember the derivative of an exponential function, you can always do logarithmic differentiation. You could even do it with a power function. I wouldn't recommend it because it's way more work than you need, but it can be done. Now, If we have something of this form, though, this is the scenario where we have to do logarithmic differentiation. You cannot use your rules of exponential functions, and you cannot use the power rule. They do not apply because these are not exponential functions nor power functions. So to find the derivative of y equals x to the x, we saw this from our warm-up the other day. This will be ln of y equals ln of x to the x. So ln of y equals x, ln of x. Now I can do the derivative of both sides. I know that this is going to become 1 over y times y prime. Here I have to do the product rule. So first times the derivative of the second plus the derivative of the first times the second. And then I can isolate the y prime. So y prime equals y times x times 1 over x is going to be 1 plus ln of x. And then my last step, I know then, that y prime, I'm just going to write it over here just to give myself more room, is x to the x times 1 plus ln of x. And so the thing that I want to emphasize that, well, that's my derivative, but this step right here, this is logarithmic differentiation because I'm taking the natural log of both sides as my first step. Here, when I have y equals u to the w, I would do the exact same thing. My derivative is going to look very similar, so I still have, notice that you still have the original function in your answer. The big difference is here I'm going to have to do the chain rule also when I do this product rule as well. Again, here, the point of this is just so that we can recognize the difference between a power function, an exponential function, and this type of function, which I don't believe has a name, but it's the input raised to another function with the same input. So basically, there's no constant in either the base or the exponent. And here we have to do logarithmic differentiation, whereas for each of these functions, we have other ways in which we can do them. This one is based off of logarithmic differentiation, and this is just the power rule.